Good morning, and welcome to the public hearing for the Harris-Galveston Subsidence District's 2024 Annual Groundwater Report. So before the meeting is open, the public hearing, I would like to address some housekeeping items. So for our in-person attendees, thank you for being here. Please be sure to silence your cell phones or smartwatches and be courteous to everyone here and online by remaining silent during the presentation. This room is equipped with microphones that are surrounding the audience that cannot be muted. You will be able to submit public testimony or ask questions at the end of the presentation. And for our virtual attendees, you will be muted for the whole hearing. And if you encounter any audio or visual problems, please type your issue in the chat for the organizer. This webinar is being recorded, including all conversations in this boardroom and all chat between online participants. So thank you for our attention. And now I'll introduce Ms. Helen Truscott, our hearing examiner, to officially open the public hearing.
Morning. Thank you, Ashley. We will go ahead and convene the public hearing for the annual groundwater hearing. Notices for this hearing were posted in both Galveston and Harris County. The notices for Harris County was posted on April 3rd, 2025 in the official county records, and it was posted in Galveston County on March 18th, 2025. As stated, any testimony this morning is being recorded, and any persons from the public are wishing to provide any additional information after the two designated speakers will be given that opportunity after they have completed their presentation. If you are going to ask a question or present any testimony, please identify yourself for the record by basically just stating your name. So at this time, we'll go ahead and convene the hearing, beginning with the Harris-Galveston Subsidence District. Thank you.
Thank you. So the Harris-Galveston Subsidence District was created by the Texas legislature in 1975 to prevent further land subsidence in Harris and Galveston counties. Land subsidence is the sinking of the land surface elevation and can contribute to flooding, infrastructure damage, and faulting. Our mission at the Subsidence District is achieved through groundwater regulation that is informed by our research and monitoring of water use, the aquifer response to groundwater pumping, and land surface deformation, as well as empowering our community to value water through water conservation tools and educational resources specifically customized for our region for everyone to use. This year also marks our 50th anniversary, so please be sure to follow us on social media and subscribe to our newsletter for updates and events. This public hearing presentation includes exhibits on the effects of groundwater withdrawals on subsidence as required by the district's Enabling Act to receive testimony on groundwater use and subsidence for the calendar year of 2024. But before I get started, I'd like to first recognize our district staff for their dedication and assistance on gathering the groundwater use data that you will be seeing here today, as well as our field representatives who help collect the subsidence data that you'll see as well. So this includes Mike Turco for his leadership, Veronica Osegueda for overseeing all the annual reports from submission to review, Ronald Giesing, Vanson Trung, Karima Hassan, Anna Scheffler, Stephanie LaFranca, Denise Lazama, and Denise Ma for entering and reviewing annual reports in our permitting software. The water use data presented in this hearing requires an enormous amount of effort from all of these individuals who step up every year beyond their usual responsibilities to compile water use data from 7,655 pumpage reports. I thank you all for your extraordinary efforts and the great teamwork to get this achieved. So this presentation includes an overview of data in these 4 sections that you see here: climate, water use, groundwater levels, and extensometer compaction data, as well as subsidence. So the first item we will go into is climate. So the district reviews precipitation data recorded from the National Oceanic and Atmospheric Administration's National Weather Service climate stations in the greater Houston-Galveston region. And this variation in local precipitation, specifically a deviation from historical normal, is important to the district because it has a direct impact on the magnitude of the total water demand from water users in this region, as well as the availability of alternative water supplies such as surface water. The location of the climate stations that were analyzed for the 2024 calendar year are provided on this map and include precipitation data from climate stations in Harris, Galveston, and Fort Bend counties. The circles and the arrow are color-coded to match the cumulative precipitation charts on both sides of the map. The 1991 through 2020 precipitation normal is a standard that was created by NOAA to show the average amount of rainfall over that time period and is a useful measure to compare against a particular year, for example, in 2024. Additionally, any blue shaded portion that you see on the graphs indicates above normal rainfall, whereas the red shaded portion indicates below normal rainfall. The majority of climate stations measured above normal precipitation for the full calendar year. And from the map and the associated graphs, all climate stations north, east, south of Houston had above average rainfall for the full calendar year of 2024. And only 2 stations experienced below average rainfall, which we can see within Katy and Hobby Airport, ending in 2024 with below average rainfall. So now that you're familiar with where they're located and how much rainfall they received, I'm going to combine them all together. So this graph marks the full calendar year from January through December of 2024, and those colors are the same colors you saw on the previous slide for those locations of climate stations. The black dashed line is the precipitation normals, which we're comparing them against. So as we can see from the graph, the majority of climate stations remained above average for the entire year, thanks to ample summer precipitation with some intermittent events in the fall. The highest cumulative rainfall was measured at Shoals Field in Galveston Island, shown as that bright green line that ends at the top with 63 inches, making it 15.5 inches above normal. The lowest total rainfall was recorded at Katy with 26 inches, placing it 23 inches below normal, as represented by that orange line. So before I show you how rainfall accumulations that you see here can affect groundwater use, I want to remind everyone that in the previous years, in 2023 and 2022, we had exceptional droughts. And a drought can really impact water use behaviors, especially during the summertime when peak irrigation occurs. So it's great to see that the majority of these climate stations have reported above normal rainfall because it lowers demand for this outdoor irrigation and increases storage in our local lakes and reservoirs that supply alternative water for our region. So now I'll review our regulatory areas and then display the total groundwater that are extracted by these regulatory areas. So here's a brief overview of our regulatory areas, which might be new to some and a refresher to others. Area 1 covers the majority of Galveston County and the Houston ship channels, including cities like Galveston, Texas City, League City, LaPorte, Baytown, and Deer Park. Permittees in Area 1 can only use 10% groundwater from their total water demand. Area 2 includes downtown Houston, parts of southern Harris County like Bel Air and South Houston, and a small northwestern slice of Galveston County like Friendswood, and east central Harris County like Channelview and Crosby. Permittees in Area 2 can use no more than 20% groundwater from their total water demand unless they have an approved groundwater reduction plan. Area 3 contains the northern and western portions of Harris County, like Jersey Village, Cypress, Spring, Tomball, Humble, Kingwood, and Katy. Permittees in Area 3 are allowed no more than 20% groundwater from their total water demand unless they also have a groundwater reduction plan. If they do have a groundwater reduction plan, they can have up to 40% of the total water demand be sourced from groundwater in the year 2025, this year, as this is a conversion year, and another future conversion in 2035 to no more than 20% groundwater of their total water demand. So now that you're familiar with our regulatory areas and their percentage of groundwater withdrawals, let's look into some of these data. So the district collects groundwater and alternative water use annually from our permittees. It provides information and understanding on how much water is being used, where it's being used, and how our permittees are using it, such as public supply, industrial use, or irrigation. This graph shows the total groundwater withdrawal grouped by use type in Regulatory Area 1. The total water demand for Area 1 for 2024 is about 17 million gallons per day, or MGD, which marks a 94% increase from the previous year. As displayed on that pie chart, the dominant water use type is industrial, which is shown in gray, increased by over 140% when compared to the previous year. And you'll notice that even with this increase in 2024, groundwater use in Area 1 has mostly plateaued since the early 1990s due to the conversion to alternative water, and it's still 88% less groundwater than was used when the district was first started, thanks to the utilization of alternative water supply. So now we're going to travel north onto Regulatory Area 2. So the total groundwater withdrawal for Area 2 in 2024 is about 26 million gallons per day, which is a 17% decrease from the previous year. The dominant water use type is public supply, that's shown in that blue color on the pie chart. And groundwater use in Area 2 has remained below 50 million gallons per day since about 1997. And the 2024 use is 84% less than the peak that we saw in the late 1970s. This decrease in groundwater use is again highlighting the district's regulations, as the majority of this area became converted to alternative water sources in 2000. So we're going to travel more north and west to Area 3. The total groundwater withdrawal for Area 3 in 2024 is about 195 million gallons per day, which marks an 11% decrease from the previous year. As shown in the graph and the pie chart, the dominant water use type is public supply, again shown in that blue, at about 95% of the total groundwater used. So I'll also point out the y-axis on this graph has changed from the previous ones because there is more withdrawal in Area 3. You also will notice some spikes in 2011 and 2022 and 2023 because those are drought years and we did see increased groundwater use. So this area consumes more groundwater than the other regulatory areas because it's still undergoing conversion to alternative sources. And in fact, effective this year in 2025, all GRP permittees must use no more than 40% groundwater of their total water demand. So now I'm going to combine all of these regulatory areas that you see here to show you the groundwater use for the entire district. So the total groundwater use in 2024 is about 238 MGD, which marks an 8% decrease from last year. And the majority is being pumped from Area 3, shown in that dark green at about 82%. Groundwater use in 2024 is almost half than what was used in 1976. And this is important because we all realize the population has grown tremendously since 1976, even though our reliance on groundwater has decreased, especially in areas 1 and 2. And this achievement is the result of successful collaborations with water providers to invest in alternative water sources and construct an expansive and plentiful infrastructure to support future growth. So we'll also explore groundwater extraction by the use type. The main water use is public supply, again shown in blue at around 88% of the total groundwater used in Harris and Galveston counties. And this should come as no surprise considering areas 2 and 3, their dominant supply was public supply. And you may be wondering how the groundwater use has decreased over time, but yet the population has increased. And again, this is possible due to the utilization of alternative water supply. So let's look a little deeper into the alternative water supply sources. So this map shows the primary surface water sources with their associated river basin and reservoir. So starting on the east side, we have the Trinity River, and through diversion canals feeds water into Lake Houston. We have the San Jacinto River, and then further west is the Brazos River. I'll also note that reclaimed water is used as an alternative water supply for the district, but it's not shown on this map because the locations are variable. Reclaimed water includes the effluent or byproduct from treatment plants, captured stormwater runoff, and reuse from industrial and irrigation processes. So let's see the total amount of alternative water used for the district. So in 2024, the total alternative water was around 856 MGD, which marks a 4.5% increase from the previous year. And as represented in this graph, the Trinity River, which is shown in that green color, has been the dominant alternative water source since the early 1990s and provided 591 MGD, which comprises almost 70% of the total alternative water used. So I'm going to combine what you see here, the alternative water used, with the groundwater use to obtain the total water demand for the district in 2024, which is about 1.1 billion gallons per day. It marks a 1.5% increase from the previous year. And the dominant water source is surface water, with the Trinity shown in that green color ranking the highest, followed by groundwater shown in blue in about 22%. So this concludes the water use section for the annual groundwater report. I'll hand it over to Mr. Jason Ramage, a hydrologist with the USGS, to review the status of the aquifers from which our groundwater is pumped to see the impact of this pumping.
Thank you, Ashley. Yeah, my name is Jason Ramage. I'm with the U.S. Geological Survey, and I'm here to present our groundwater level data for 2025, groundwater level altitudes and short and long-term changes in the Chico Evangeline, undifferentiated aquifer, and Jasper aquifer. We'll also be looking at compaction data here today. I'd like to thank the district for having us here to present today, and for their continued efforts these supporting us in these data collection efforts, as well as our other cooperators here shown on the slide. Other cooperators include the Fort Bend Subsidence District, City of Houston, Lone Star Groundwater Conservation District, and Brazoria County Groundwater Conservation District. Okay, so some of the items that will be covered here today, we'll be looking at the 2025 water level altitudes for the Chico Evangeline, undifferentiated aquifer, and Jasper aquifer. We'll also be looking at 1-year and 5-year water level changes. And then we'll look at longer term changes since 1977 for the Chico and Evangeline, and since 2000 for the Jasper. And then I have a couple of slides on compaction data as well. Briefly, before we get into the data, just a quick overview here of the hydrology and the aquifers here in the Gulf Coast aquifer system within the greater Houston region. So this figure on the right-hand side, this is a sort of simplified depiction of the cross-section of the aquifer system here, beginning in Grimes County at A and reaching down to the coast. This is a cross-section which is approximately perpendicular to the dip direction. And so as we can see that these units, they thicken towards the coast region here. These are sediments which are made up of primarily coarse grains, sands and gravels, interbedded with finer grains, silts and clays. So here we see we have a shallower system, the Chico and Evangeline undifferentiated, and then we have a deeper aquifer, the Jasper aquifer. Between those two units is the Burkeville confining unit. This is a thick layer, relatively thick layer of fine grade sediments, which separates the heads between the two aquifers. So a few items about our network. We're collecting data in wells which span 11 counties. This includes Harris County, all of the immediately adjacent counties, as well as some portions of Grimes County, Walker County, and San Jacinto County. We began our data collection December 3rd, and we completed our data collection on March 13th. We typically collect our data during this time period when the aquifer systems are experience the least amount of stress from pumping. And then the network is made up primarily of public supply wells. We also have a mixture of irrigation, industrial, and observation wells. So we have 562 wells, which are screened in the Chico and Evangeline undifferentiated, 112 wells, which are screened in the Jasper. To produce this year's water level altitudes, we used 500 and water levels from 525 wells. And just to note that 39 of those use water level data, which were estimated. And then for the Jasper, we used 108 water levels. And then similarly from that, 15 of those were water level data, which were estimated. Okay, this slide is showing the water level altitude for the Chico and Evangeline undifferentiated for 2025. What this map represents are water levels which are either above or below the NAVD 88 datum. So if you were to project the plane effectively of sea level landward, these water levels are either above or below that plane. And so warmer colors represent water levels below that datum, and then the cooler colors represent water levels above that datum. And we can see that most of the study area here is has water levels which are below that datum across most of Harris County over into portions of Liberty and Chambers County, as well as Galveston, Brazoria, and Fort Bend, parts of Waller County. Some of the largest, some of the lowest water level altitudes are in the western portions of Harris County, small areas of northwest Harris County, northern Harris County, and then and those water level altitudes are between 250 and 300 feet below datum. And then we have an area of southern Montgomery County there of a little bit more than 300 feet below NAVD 88 datum. And then as we start moving more towards the north and the west, out towards the margins of the study area, we see these water level altitudes above datum. Looking at 1 year water level changes. So these are changes in water levels from 2024 to 2025. Primarily, most of the water levels were represented as water level rises, and these are in the map figure here. These are the upward facing triangles in cooler colors. So about 47, the lower 47% of water levels were rises from the previous year. Of those rises, about 63% were in that 1 to 10 foot range. This is kind of typical for what we see for most years in that 1 year time period. Some of the largest rises were of more than 40 feet. There were 2 wells in Montgomery County, one here, kind of in central Montgomery County, and then another here in southern Montgomery County. And then about 38% of water levels were declines. And those are represented here on the map as the downward facing triangles in the warmer colors. And so some of the largest declines of more than 40 feet, there were 2 wells in Fort Bend County, one in northern Fort Bend County and one here in more in central Fort Bend. So moving on to 5-year water level changes since 2020. The majority of these were water level declines, a little more than 87%. Of those declines, 69% were in that 1 to 20 foot range. And we can see those are represented across most of the study area here. Some of the largest declines were in portions of southern Montgomery County, northwestern and western Harris County, as well as some in northern Fort Bend County. And then about 10%, a little over 10% of water level changes were rises, and those rises were also in some of the same areas in southern Montgomery County, primarily western portion of Harris County and Fort Bend County. Some of the largest rises, there were 2 wells of more than 30 feet of rise in western and eastern Montgomery County. Again, similar areas to what we saw for the 1-year changes. Now we're looking at long-term changes for the Chico Evangeline since 1977. These are water level rises or declines since that time period. So the cooler colors are water level rises, the warmer colors are declines. And we can see that most of central and eastern Harris County, as well as portions of Galveston County, Brazoria County, even into Chambers and Liberty County, we see these water level rises. Some of the largest rises occur in a portion of east central Harris County, kind of near the Pasadena area here, where we see rises of more than 180 feet. And then as we start moving more towards the west and the north, we transition to these water level declines. And some of the largest declines are in portions of western and northern Harris County, where we see declines of between 300 and 360 feet. And then we've got areas of south central Montgomery County, where we see declines of a bit more than 360 feet. Okay, moving on to the Jasper. This is the 2025 water level altitude for the Jasper. Again, these are water levels which are referenced either above or below that NAVD 88 plane, or excuse me, datum. Generally, we see this trend of deepening water level altitudes in the down dip direction. And some of the largest, or excuse me, some of the deepest, hit the wrong button. And some of the deepest water level altitudes are in a small area of south central Montgomery County and dipping into a portion of north central Harris County here. Those water level altitudes are just a little bit more than 250 feet below NAVD datum. And then again, as we start moving in the up dip direction towards the north and the west, we see these water level altitudes above datum in the cooler colors here. And then we have two of our further south Jasper wells, which is represented or labeled here as point values. We have one well in a monitoring well in Harris County at the south end of Lake Houston. It was 42.9 feet below datum. And then we have another a public supply well here in Fort Bend County, which was 35.6 feet above datum. Looking at the 1-year changes now for the Jasper, we had about 57% of these were declines, while 38% were rises. Most of the changes, either both rise and decline, occurred in that 1 to 10 foot range. We had some of the largest declines of more than 40 feet, and we had one in Northwest Harris County here, and one in one here in central Montgomery County. And then two wells showed the largest rises of more than 30 feet. One here in central Montgomery County, and then another in south central Montgomery County. Now looking at 5-year changes, almost all of these, are about 90%, show water level declines for the period. We had about 9% which showed rises, and then only one well showed no change. So these, many of the declines that we could see here, there are quite a few which showed declines of more than 50 feet in portions of central Montgomery County, south central Montgomery County, as well as a few in northern Harris County. Now looking at long-term change in the Jasper, this has changed since 2000. These are water level rises or declines since that time period. Generally, you see water level declines across most of the study area, except for some of the furthest areas to the north and west, sort of extreme northwest Montgomery County and portions of Grimes County here. And then looking at some of the largest declines for this time period. There's an area of southern Montgomery County here and south, which have shown declines of more than 200 feet since the 2000 time period. All right, so moving on to compaction. So we have 14 extensometers across the region, primarily in Harris County. We do have one here at Texas City and Galveston County. One that is not being shown here currently today is the Cinco Mud extensometer, which is in Fort Bend. We are currently looking into an issue with that extensometer into the accuracy of those data. So I do not have those presented here today. But what this slide shows are the locations of those extensometers, the size of the symbol is proportional to the total amount of compaction recorded at those locations since the beginning of their record. On the left-hand side here, the dates of data recording at each of these locations is listed here. And then the total amount of compaction is also listed here in addition to on the map. So for instance, Addict's extensometer here has recorded the most amount of compaction for this year, 3.885 feet. And then Texas City is a cumulative compaction of 0.119 feet. So we have two at Baytown, and I didn't have it labeled here. So we have a Baytown Deep and a Baytown Shallow here, similarly to Clear Lake Deep and Clear Lake Shallow. Another note here is that the colors of these symbols represent the portion of the Chico Evangeline in which it is recording compaction. So the sort of blue or purple circles here are representing those extensometers measuring compaction within the Chico portion of Chico and Evangeline. And then the red symbols here are measuring compaction within both the Chico and Evangeline. And then finally, this slide shows the amount of either compaction or expansion, which was recorded from December 23 to December of 2024. Almost all of our compaction sites recorded compaction with the exception of our northeast extensometer, which recorded 0.07 feet of expansion. Our range of compaction ranged from, again, 0.07 feet of expansion to as much as 0.063 feet of compaction, which occurred at our Baytown Shallow extensometer. The two Baytown sites recorded the most amount of compaction. Most of the rest of these extensometers recorded very little compaction for the year. And with that, that's all I have. Thank you, Ashley.
Thank you, Jason. All right, so we will conclude with subsidence. So the district uses GPS stations installed throughout our jurisdiction in some adjacent counties to collect GPS data to monitor changes in the land surface. And the schematic on the right displays the design of our station, which includes a 2-inch pipe that's drilled to about 34 feet total depth, also extends 8 feet above the land surface in order to hold an antenna that is mounted on the top. It's protected by bollards and includes a separate pipe that holds an enclosure box, which stores the receiver, battery, and other power-related equipment. And then all the pipes are secured and surrounded on a concrete pad. So these stations collect GPS data in all 3 dimensions. So that's 2 in the horizontal, north, south, east, and west, and then the vertical direction or up and down, which we use to track land surface movements. And the data are collected at each station for approximately 1 week every 2 months. And we recently began a conversion in monitoring from this periodic monitoring to continuous, meaning that the equipment will collect the data every single day of the year. This conversion to cores happened in 2023 and is projected to be completed in 2027. So now we'll look at the subsidence monitoring network. As I mentioned, we collect GPS data from our stations, but we also work with collaborators who have their own GPS stations to receive information on the land surface elevation. These stations are stretched across 20 counties in Southeast Texas, and this map shows the location of the station and is differentiated by the operator. The Subsidence Monitoring Network includes a collaboration between the Subsidence districts, the University of Houston, and adjacent groundwater conservation districts, as well as the Texas Department of Transportation and other local agencies. The district is shown in that dark blue triangle and currently maintains 74 stations. So now we'll take a look at what the data collected at these stations looks like. This is our annual subsidence rate. It is a linear regression, or basically the best fit line of GPS data points for the ellipsoidal height, was just the up and down direction that primarily we're interested in. We estimate a 5-year rate of change for the annual subsidence rate from 2020 through 2024 from processed GPS data collected at these stations and processed by the University of Houston. The stations shown have at least 3 or more years of monitoring, and we're also actively monitoring in 2024. The subsidence rate is displayed as a circle that varies both in size and color according to the rate. So the warmer and larger circles show higher subsidence rates, and the small green circle represents lower subsidence rates to even uplift in some areas. The areas with the greatest subsidence rates, again, that large red circle, are observed in Area 3, particularly in western and northern Harris County, in the Katy and Spring area, as well as northern Fort Bend County in the Cinco Ranch Fulshear area, and southeastern Fort Bend County near Arcola, as well as in southern Montgomery County in the Woodlands. Regulatory areas 1 and 2 contain majority of small green circles that represent less than ½ centimeter of subsidence, which is approximately the rate of natural subsidence and within the range of our equipment accuracy. Therefore, these areas, which are fully converted, mostly converted to alternative water sources, measured little to no subsidence, and even some show minor uplift. So now I'll show you what the data looks like behind these points. So this is GPS station MRHK. It is operated by the University of Houston and is located in Katy. It's marked as that blue triangle on that inset map. It began monitoring changes in the land surface in 2014 and has measured a total subsidence of about 18 centimeters or about 7 inches over this decade of monitoring. The period of record plot is a time series displacement scatter plot that you see on the top right, and includes both the processed GPS data points as well as an outlier boundary, which is shown in that red dashed line, to show data points that are identified as outliers in the red circles. The valid GPS data shown in those gray small circles are used when we calculate subsidence rates. And the bottom bar graph shows the 5-year subsidence rate over the period of record, or the time it has been monitoring. MRHK has a subsidence rate of around 2 centimeters per year, which is close to about 1 inch per year. And now I'll show, for the first time ever in the annual Groundwater Report public hearing, I'm very pleased to show you how the district monitors in between those GPS stations that you saw on that first map. So before I do, I'm going to give you an overview of what you'll be seeing so you can hopefully better understand the map. The district has used other remote sensing technologies to investigate changes in the land surface. It enables us to see changes that occur in between those GPS stations that are scattered across the counties, or those colored circles that you saw on the previous maps. Since 2019, with help from the experts at Southern Methodist University, and more recently, with experts from the Conrad Blucher Institute of Texas A&M Corpus Christi, the district has used interferometric synthetic aperture radar, INSAR for short, to better understand subsidence in our region. This is an overview of how INSAR works and the data products obtained from these sensors that are orbiting the Earth. So SAR data are created through the transmission of electromagnetic radiation, or basically radio waves, that are sent from the sensor to the ground surface and then bounce back up to the sensor. And the image on the left illustrates this with the red color bands that are traveling down and then the green bands that are heading back up to the sensor. The sensor circles the Earth in a precise orbit and time called passes. It takes about 12 days for the sensor to revisit an area that was previously captured. So in this image, there's about 12 days between pass 1 and pass 2. And experts can use this information gleaned from these series of different passes, for example, comparing pass 1 and pass 2, to detect small changes in the distances between them. This processed pair of SAR images is called an interferogram and shows if the land is moving up or down. This process shown on the right image, an example that is sourced from the USGS fact sheet for an area in California. And what I want to show is the top map shows a 2D interferogram, which has red colors as subsidence, or the land is sinking down, as much as 3 centimeters, and the blue colors are depicting uplift, where the land is moving up. In order to better visualize what this 2D map is doing, they also created a 3D topography map that you can really see the red as sinking down and the blue as rising up. Of course, it's also greatly exaggerated in the vertical direction, but it's done so you can understand what those colors mean on the 2D surface. And this same process has been applied to our region, and with state-of-the-art processing techniques can be applied to achieve accuracy in the millimeters. So here it is, subsidence rates from INSAR. This map shows the annual subsidence rate averaged from 2000 to 2024 in the Southeast Texas Gulf Coast region. I'm using the same color ramp and subsidence rate interval as was previously shown on our GPS station data, where the warmer colors indicate greater subsidence, and the green shows minimal subsidence to uplift. And you'll notice that it closely resembles the GPS station data, such that areas 1 and 2 are mostly green, which is good. There's no major subsidence being measured. The reds are concentrated around the Katy area in western Harris County, northern Fort Bend County, and then stretches along Cypress and Spring in northern Harris County into southern Montgomery County around Highway I-45. Isolated areas of subsidence are also recorded in that Manville, Iowa colony area in northern Brazoria County, as well as a pocket in Mont Belvieu in western Chambers County. So this concludes the subsidence section of our annual groundwater report. Thank you for your attention. I'll turn it over to Ms. Trescott for public testimony and comment.
The notice for this hearing was given to all county municipal governments, all interested persons, and all water well owners in Harris and Galveston counties. And the notice stated that the purpose of this hearing is for considering testimony, evidence, exhibits, and other information presented by any person concerning the effects of groundwater withdrawal on the subsidence of land within the district during the preceding groundwater withdrawal year. So at this time, if there are any persons in attendance that would like to present any testimony, evidence, and exhibits concerning any groundwater withdrawal during this previous year, this is your time. Okay. If you're not able or prepared to present your testimony at this time, we will keep the record open until May 7th to receive any additional documents, or exhibits, or information. If you'd like to submit that information, you just can contact anyone here at the district, primarily Ashley, and that will be included in the report. The report will be presented and available after it has been completed and accepted by the board. Are there any questions for either of the presenters for today?
Yes, thank you for your question. This hearing that you see on the presentation was actually uploaded to our website yesterday and is available on our website. If you go to hgsubsidence.org, and then in the upper bar, there's science and research. So if you click on that section, there's a drop down for annual groundwater reports. That will take you directly to the page with the link for the presentation. And that will be the same area once this is released. I'll go to the next one. So as Ms. Trethcott mentioned, on May 7th, the record will close, and you can send us comments at info@subsidence.org. Once we present this to our board on May 14th for their approval, we will post the results of the report and an executive summary, as well as an interactive map to our website in that same location that you can find this hearing presentation. And you can also scan this QR code if you have your phone available, and that will take you directly there.